calculus 3. And this part, we will continue work on partial derivatives. And essentially, partial derivatives are derivatives. So all the derivative rules you learned, they continue to work. And we did, I guess, at least 2 examples, right? Some of them are pretty big. And I guess if you don't see the idea, it might be very complicated how we can handle the situation like these things. But if you understand the idea, I say they are very straightforward calculation, and also it is really important you do understand. You do need to know those derivative rules, formulas very well. Partial derivatives are derivatives. Okay. And for this time, we move a little further. Maybe before I move further, we can take a quick look. Partial derivatives, they are created for function of multivariables. So I'm saying you understand that this is g sub x, partial derivative with respect to x. According to the result we generated, it is still a function of multivariables, right? 3 variables. So accordingly, we can continue to get the partial derivatives of this partial derivative. Same for the other partial derivative and this one and all the partial derivatives. So I'm saying the partial derivatives of the partial derivatives, they are the so-called higher order partial derivatives. That is the same. That is the same. Again, the way to calculate the higher order partial derivatives, you are going to know those derivative rules very well. So this is the example from the textbook again, 4.19. We are just doing a function of 2 variables, f of x and y. So first, we do know there is f sub x and f sub y. Hopefully, let me double check. I believe I should be all right. F partial derivative with respect to x, this exponential term is a constant times x. And the sine tends to be cosine, then partial derivative with respect to x. From this part, we got a 2 here. Then partial derivative with respect to y, see it very closely. This is an exponential function. The x still stays. We got a negative 3 from the chain rule. So it is negative 3x times e to the negative 3y. And then derivative sine still tends to be cosine. But the derivative of the inner part, it is with respect to y. So I got this minus 5 here. So far to this moment, really it is another good example for partial derivatives. And each partial derivative, it is function of 2 variables, right? So we can calculate the partial derivatives for each. And each, there are 2 partial derivatives. And indeed, there are together, these 2 partial derivatives together, they will give 4 second-order partial derivatives. How about let's take a quick look how the partial derivatives would look like. Starting f sub x, we can continue to calculate the partial derivative with respect to x again. So it is written as fxx. Then it using the d dx notation, it is d2f dx2. Okay, I'm talking about this line here, partial derivative with respect to again. This is a constant derivative 0. This part, cosine, it is changing back to sine. Actually, I should say it precisely negative sign. The 2 stays, but there's another 2 coming out from this inner part. That's from the chain rule. So this is what I got. It tends to be negative 4 sine of the function. fxx. And this fx, it is function of 2 variables. We could do the partial derivative with respect to x, and also we could do the partial derivative with respect to y. So that will be denoted as fxy. And using the dd notation, it is d2f dy dx. Okay, I'm still working on this term. partial derivative with respect to y, that's negative 3 times e to the negative 3y, right? Chain rule. Partial derivative with respect back to y to about this term, the two-stage derivative cosine tends to be negative sign. And from the inside, we have another negative 5. That's from the chain rule. So fxy it tends to be such. The first one, it is second order partial derivative by taking derivative with respect to x 2 times. The second one, it is also second order partial derivative by taking partial derivative with respect to x first, then with respect to y. By the way, the answers are different, right? And similarly, look at, we do have another first order partial derivative, f sub y. It's a function of two variables. So accordingly, we can do partial derivative with respect to x and the partial derivative with respect to y again. So I did my calculation. Still, first of all, take a look if notation-wise makes sense. fyx, it's d2f dx dy. So I'm looking at this part. It is taking the partial derivative with respect to x, negative 3 times e to the negative 3y, right? And then starting from negative 5, cosine tends to be negative sign. Then from the derivative inside chain rule, we got a 2 here, right? So that is what I calculated f sub yx. And if you are sharp enough, or really, if you take a just close look, you may see a surprise. I mean, fxy, fyx, they look like the same, right? They are the same. And also, I want you to know it's not just by chance. It has to be in this way. And then we will present the formal conclusion just in a moment. Okay. It had to be in this way. And still, let's take a look at f sub y again. I did fyx already. And indeed, I could consider partial derivative with respect to y again, fyy. So this is fyy. Okay, it's starting from here, fyy. So negative 3x stays, and you have another negative 3 from the chain rule. Certainly the exponential term stays as it is. And the second term, negative 5 stays. Derivative cosine tends to be negative sign. With respect to y, there's another negative 5 out. So that is what I got for fyy. This time there was, well, for the first part, negative 3, negative, that's plus. And for the next part, second term, we have 3 minus sign, so still the minus. This is what I got, fyy. So in general, it is just true. When you have a function of two variables, there are 2 first-order partial derivatives, and there are 4 second-order partial derivatives. And a very important result you may want to know, fxy, fyx, they are the same. They are the same. And this formal conclusion, it is called as Cradle theorem. And I think that should be it about my presentation on section 4.3, partial derivatives. Thank you for watching.